My name is James, and I'm going to be talking about a library I've been writing called Zelkova. This is an 800-year-old Zelkova tree. It's living at a shrine in Japan. The Zelkova trees are in the same family as elm trees. Zelkova, the library, is basically a reimplementation of parts of a language called Elm into Clojure and ClojureScript. Elm was made by this guy, Evan Czaplicki. He did his senior thesis a few years ago on this language that he made. It targets the browser, and it's specifically for building graphical user interfaces with functional reactive programming. Elm is really fun. Bodil Stoka at Strange Loop last year described it as if Haskell were designed by a usability expert. So it's pretty nice. So there's lots of different kinds of FRP out there, functional reactive programming. If you're curious about how Elm's model of it relates with other kinds, then I highly recommend Evan's talk from Strange Loop last year, Controlling Time and Space. He really goes into the trade-offs in a good way. But Zelkova is based on Elm's version of FRP, and so it's really all about signals. What is a signal in this case? It's a value that changes over time. In the Clojure community, though, we have this really strong separation between values and identity. Rich has made this very clear to us all, and we have this notion that a value is just an inert, immutable snapshot in time, and that an identity has different states of different values over time. So what are signals? Are they values or identities? Well, I like to think of signals as values which represent identities. In all the ways that are really useful when you're working with signals in Elm or Zelkova, they are immutable. You can pass them around and not worry about anyone else messing with them and screwing up your code. But they do represent a sequence of values over time. This is kind of what makes them cool. So I'm going to get into a demo. OK, so I'm going to show you a little flyer game, not quite a game, but the beginning of one. Here's the beginning of it. I'm using Quill to do the rendering. Quill has its own ways of doing managing events coming in, but we're going to use Zelkova for that part, just to show how it works. OK, so just to show you the code that's already here, I won't get into the Quill rendering code too much, but basically it's just drawing this triangle on the screen, and it has state that Quill manages in an atom. And I have this namespace of some vector math functions to use, things like converting into angles in radians or messing with the magnitude. So we're going to use that for some geometry. But most of the code I'm going to put into this namespace, my signal namespace. And I've already included some, I've required some of Zelkova's namespaces. For this one, we're just going to be using the mouse and the core signal namespace, which I typically alias as Z for Zelkova. OK, so let's get started. Just to show you putting something on screen, I'm just going to get the ship to follow the mouse for now, just to be quick about things. So here we're going to make a steering function. Eventually it's going to like steer the ship, but right now it's just the ship is just going to follow the mouse. It's going to take a state of the shape that we have over here. It's flyer with position, angle, velocity, and mouse position, which is going to be a vector of x and y. And so we're just gonna, so send state flyer. Okay, so we're just updating the flyer position with the mouse position. And we're going to write this app signal function, which is going to take in an initial state and return a Zelkova signal. For this game, we are going to want to manage the state in Zelkova and be able to change the state based on, like update it using a reducer function, basically. So I'll show you how this works in Zelkova. We have this reductions function. If you're used to Elm, this is like fold P, except its arguments are reversed, so it plays nice with Clojure. So right now we're just going to take in steering. Maybe I'll just, yeah. Okay. Steering, the initial state, and mouse position. And mouse position is itself a signal. And I don't need to call it as a function to get the signal. It's just already a signal. And the namespace provides it. And because it's just an immutable value, it's fine. It can be shared by different signal graphs. I might have a bunch of them going on. But for now, we're just doing one. And basically what this is going to do is it's going to take the initial state, reduce, basically the reductions signal becomes a signal of successive applications of this steering function on the state with incoming mouse positions. So here, to wire it into our Quill sketch, I'm going to take the initial state, call that app signal function to get a Zelkova signal from it. And then I'm going to use this pipe to atom function, which is going to take all the values from the signal and just reset the atom that you give it. So here I'm using the state atom that Quill has baked in. Okay, so let's see if this does something. Yeah, okay, so here we have it following the mouse. So it's a start. Okay. I'll go back to the signal namespace, and now I'm going to make it so that it's actually going to steer instead. So the first thing I'll do is I'll get the flyer position, because we do need that to figure out the angles. Then I'll get like a difference vector. So I'll use my vector math namespace and subtract the mouse position from the flyer position to get an offset. And I'll calculate the angle with my vector deradians function. And then I will change this associan to update the angle instead, and then I'll update the angle. Yeah, like that. Okay, so already I can see that this is too boring for Tuesday morning. So I'm going to get an image that I have for the flyer, just so that it's not a boring triangle. And then, let's see, down here, I'm going to get that out of the state of the flyer, and then get rid of the triangle. Oops. Okay, so there. Okay, so here's our flyer now. It's a little bit better, but it's it's a little big, and it's not pointed in the right direction, really. So I'm just going to let's see. I'm going to rotate a little bit more. Good. And I'm going to scale it down a little bit. We don't want him that huge. Ah, good. Okay. So, okay, now we want to move Rich around. So we're going to add a new function that's going to update the state similar to steering, but it's going to be thrust this time. So it's going to take a state and a Boolean value of just whether or not we're going or not. So we're going to do something. We're going to do some calculations if the toggle is on. So we're going to get the angle from the flyer. And then we're going to update the state, update the position of the flyer in the state. Oops. And the way we're going to do that is we're going to take the angle, we're going to convert it into a vector, like, so it'll just be like coordinates in whatever direction you're in. And then we're going to add that to the current position. So we're just going to, wherever your mouse is pointing, the thrust is just going to go in that direction by like 1 unit. So to wire this in, we're going to do, basically, at this point, we have mouse position, and we want to be able to control thrust somehow. So I'm gonna bring in the keyboard. I lied before. We actually do need another namespace. Oops. Okay, so we have the keyboard now, and we need to bring those together. So in Zelkova, you can use the map function of Zelkova. It's not the regular map function. And it has the same basic function signature as in Clojure core. So you can pass it multiple signals to get values from, in the same way that in Clojure core's map you can pass multiple collections to get values from. And in this case, our mapping function is going to be vector. So we're going to take the keyboard space signal, which gives you a Boolean of whether or not the space bar is down, and the mouse position, and then map them into vectors. So anytime either one of those signals updates, this map signal is going to update as a vector of the two current ones, the current space being depressed and the current mouse position. So we're going to call that inputs. And then we're going to put it in here. And we need to change this reducing function passed to reductions to be, instead of steering, it needs to be something that knows about these vectors. So it's going to take the state and a vector of spacebar and mouse position, and then it's going to thread the state through the thrust function, passing it the second argument of the toggle, and also thread it through the steering function. Okay, I think this should work now. Okay. Oh. What do I have wrong? So here, I forgot the else clause of the if, so it just got rid of the state entirely. Anyway, So I need to say, don't do anything to the state if we don't have the spacebar depressed. OK, so so now he can move around, but it's there's something weird. Well, OK, the problem is that every time I hit the spacebar, no matter how long I hold it down, it's just like 1 pixel. So, but if I move the mouse, then it does that. So what's going on here is that the map function in Zelkova is it's updating whenever either of the inputs are updating, and the spacebar input only updates when it changes. So, but the mouse position changes whenever the mouse moves. So he can go as long as the mouse is moving, or he can go like that, but not otherwise. So the way we're going to fix that is we're going to use a clock. So yet another namespace I forgot about. So we need time. Elm and Zelkova have it's a pretty good model for working with time. So you can do, there's a few different things in this namespace, but the one we're going to use here is FPS. So FPS is going to take the number you give it as a number of frames per second. It's going to give you a signal that updates that many times per second with the delta in milliseconds from the last time it updated. So we're going to use that. We're going to just slot it into at the beginning of that vector. We're going to let our reductions function know about it. And then that should be good enough to at least let me hold the spacebar down. OK. OK. But we want to be a little bit more realistic with our game, or at least it needs some physics. It's not going to be the most real physics in the world, but it'll be some kind of physics. So we're going to, instead of talking just about thrust as some fake, constant thing, we're going to instead talk about acceleration. So we're going to rename it to acceleration, and we're going to have, let's see. So instead of updating the position, we're going to update the velocity. And right now that wouldn't do anything, but we're going to add another little bit of physics called inertia. It's going to take a state and a time delta this time. So we're going to calculate a translation to figure out how we should move the ship. So we're going to multiply the velocity by the time delta to figure out how much time has passed, so how much we should move the ship. OK, so now that we have inertia, so and this is just using vector addition to translate the current position. So now that we have acceleration, we're going to, and inertia now, we're going to put the inertia in here, threading it into our little pipeline. Give it the time delta, and whoop! Oh, ooh, that's really quick. OK, we need to do some tweaking here. Okay, so clearly we need to multiply some more. So here it is. Ooh, slightly more manageable, but okay. So this time, every frame we translate a little bit less, but the acceleration is still pretty wild. So I'm going to put a limit on it. I'm going to limit the magnitude of the vector that we end up with for the velocity. So we're going to limit the velocity to 1. So we're going to just think in, like 1 is the max, and you do, yeah, oh, yeah, okay, that's, okay. So that's still, that's better, but it still feels a bit weird. So the problem is that right now it's limiting to 1, but actually it's starting at 1 too, I think, because we start with a normalized vector. So we need to just take the vector that we're adding to the velocity, the thrust that we end up with. We're going to make it a magnitude of 0.2 always. So every frame that you're accelerating, it's only going to increase the velocity by a magnitude of 0.2. And then that's a little bit better, but there's something weird going on here. You can see how every time I move my mouse, it goes faster. Okay, so what's going on here is that we still have this map signal updating every time any of the inputs updates, which means that, and the value at any given point in time includes, the fresh value of one of these signals, which just updated, but also the previous values of the others. And we thread through all of these different things, inertia, acceleration, and steering, every time. So what's happening is that we are calculating inertia not just every clock tick, but every time the mouse moves as well. So what we need to do is take this signal and use another function in Zelkova called sample on. And we're going to sample it on the time delta signal. So we have this signal of vectors with all our inputs, and instead of just getting all of them, we're only going to sample the current value of that every time the clock ticks. So everything is mediated by the ticker now. And now, no matter how fast I move my mouse, he's not going to go any faster. Yeah. Okay, so that's the end of this demo. Okay. Okay, so that was good fun. So this is basically the graph of signals that we made. So we can see that this is like pretty much everything good in the world. It's a directed acyclic graph. And you might be wondering, now, why not just use core async? So core async is, you can manage incoming events with core async. You can merge channels together. There's a bunch of good functions in core async to help you with all that. Well, Zelkova is using it. It's implemented in core async. So what happens is when you use the pipe to atom function, for example, it spins up like a live graph of basically core async mults that are, so mults let you emit values to multiple other channels. So Zelkova, currently the implementation is that it uses core async mults behind the scenes to wire everything up. This red splotchiness is basically just event propagation. Things are moving. And in fact, you can take the same Zelkova signal and produce multiple live running graphs from it because the signals are just immutable values. So they're like recipes for spinning up live graphs. Here's another way of getting at an actual live graph object from Zelkova. You can use the spawn function, and then live graphs conform to the core async mult interface or protocol. So you can use the core async tap function to tap a live graph onto multiple channels if you want. Okay, so why not just use core async though? I mean, it's built on core async, but why do we need this? So the reason why it's good is that signals are values transformed by pure functions. They can be shared freely with different parts of your code. And the signal graph is synchronous and deterministic. I don't get too much into that aspect in this talk. Evan does in controlling time and space more. But basically, we use core async to get this synchronicity. But if you do it on your own with a graph that has diamonds in it and everything, then it's not obvious necessarily how to do it. And it's Zelkova basically does all that work for you. So we can push mutation to the edges and get a reasonable language for talking about time. This is something that I think is one of the big strengths of Elm. Okay, so we've played around with a fun little game, but now it's time to get down to business. Okay, so a lot of people look at Elm and they see a lot of games in the demos, and they think that it's kind of a toy language sometimes. Building big applications in Elm is definitely an area of active research, but Evan has been, and others have been putting a lot of time and effort into figuring out and exploring this space. There's a great GitHub repo that Evan has on how to structure larger applications in Elm, and it's a really interesting what they're coming up with. But for the demo that I'm going to do right now, I'm just going to instead of doing like a big application all with Zelkova, I'm going to instead have an Om component and show you how you can use Zelkova to have a signal graph operating on an Om component. So you can just use like a little sprinkle of Zelkova when you want some nice event coordination stuff. Okay. Okay, so I have a project here. It's got some code in it already. Basically, what we're going to do is have a little Wikipedia search field that we're going to show some autocomplete suggestions underneath. It's not going to be very full-featured. It's just going to show you how we can get some benefit from Zelkova with Om and other libraries like it, like Reagent and Quiescent. Okay, so right now this is just a template. There's nothing going on there. So that's the HTML for the template. And we have a couple functions that I'm going to be using. So here is how we can convert a search query into a JSONP request for Wikipedia. Here's a utility function to take a channel and merge its values into an Om cursor. So here you can see we're using the Clojure core merge function to do that. And here is just a convenience function for turning a channel into an input DOM handler that will put the current value of the input field onto the channel. Okay, and okay. So there is, oh yeah, okay, so there's one other namespace that we have with some JSONP stuff. So to talk to Wikipedia, we're going to be using, do I have internet? Oh, okay. I do have a backup plan. Is the Wi-Fi on? Yeah? Okay. Let's see. Ah, that's the problem. Okay. Ooh, okay, great. So, okay, so I'm not going to get into this code too much, but basically this function is a JSONP pipeline, we're calling it. So it takes two channels, core async channels, from channel and a to channel. So from is going to be a channel of requests, which are going to be maps that have URL and params keys in them. And then to channel is just some other channel that you want to eventually get responses on. And so we use the Google Clojure libraries to do some JSONP. We convert back and forth between Clojure data structures and JavaScript. And one other important thing that we do is we attach the original request as metadata onto the response. Then here we have a function called fetchResponses. And with this one, we're going to take in a Zelkova signal of requests and return a signal of responses. So we're using the splice function here. And the gist of that basically is that we get to tap into the signal graph on the level of core async channels. And we end up with a signal that ends up being not synchronized with the rest of the signals, but instead it's like an asynchronous signal. So it's as if it's another source of input events like mouse position. So the responses could come at any time. Okay. Okay, so let's get started. So we want to wire this up so that when we type stuff in, we're going to get Zelkova to do stuff. So the first thing I'll do is start with some state on this Om component. So the first thing we're going to do is make a Zelkova write port. So a write port is a kind of signal. This is a signal constructor in Zelkova. But the signal that you get back, you can also treat it like a core async channel. This is kind of a gray area with, like, is this really an immutable value anymore? Because you can push values onto it. But the important thing is that this signal can be shared between multiple running graphs. So you could have multiple graphs that share structure, and you can be putting values onto one of the write ports, and every graph gets it. They don't compete for the values. Okay, so we're going to initialize this write port with the text in the Om props. So this is like an Om cursor that we get, and it has a text field that we're going to initialize the write port with. And then the state that we're going to return here as the initial state of the component is it's going to have an input handler that the text field is going to use. So we're going to initialize, we're going to use that function that I mentioned before, channel input handler. We're going to pass it the write port, which can act as a channel. And we get back a handler that the input can use. And then the other thing is we're going to just have a key called signal, which is going to be like the main signal of the component. And that signal is going to be, we're going to say, we're going to take in the, okay. We're going to take in the text that we get from the text input and return a map of text to text, okay? It'll still become a little bit clearer in a second. We're going to implement the will mount protocol of Om so that, so this is where we're going to wire things up. So far we just have inert signals, but we're going to now take these signals and hook them into the component. So we're going to get the signal from the state. We're going to call another Zelkova function. This is like another convenience function like pipe to atom, but in this case, it just gives you a channel, a core async channel back. So we're going to turn the signal into a channel that we can get values from that way, and then we're going to merge channel values into the cursor. Okay, not quite done this iteration yet, so the other things, we need to do a couple other things. So one is we need to get the text from the cursor and bind that to the input field's value. And then we want to attach this text input handler to to the input. And just to show that things are actually doing something, instead of this text here, we'll use text from the cursor. Okay, so it's doing something. So that's how we can wire up the state. And because I only have a couple minutes left, I'm going to just jump to the end and show you how this works. So okay. So basically, this is the final result. But basically, we end up using the debounce function that Zelkova provides to debounce the input. We fetch responses. We drop the stale ones by checking the metadata of the response against the last request that was sent out. And the end result is that we can actually search Wikipedia. Okay. I also have a reagent version of this, which I don't have time to show, but I will have it online so you can see that too. All right, so Zelkova is on GitHub. It's on Clojure's. I just pushed 040 last night. It's got the functions that I was using today. There's a to-do MVC demo. There's a Mario demo, which is a port of the Elm version. And there's this drag and drop demo that shows you drag and drop and shows you has a output of the state there of the final signal. And also, I wanted to give a shout out to Dan Luttrell Porter, who is also giving a talk at Clojure West, and he actually has the, as far as I know, the first production deploy of Zelkova, and it's this magic card deck building thing, and he uses it for the drag and drop. Okay, so things to do for Zelkova. I want to make it so that the state of the signal graph, the running graph, is exposed. This will make it better for using it with Figwheel and just better in other ways. I have been thinking of ways of compiling a signal to a transducer of events to output values. That's going to also play in with how I externalize the state. Elm has a fantastic time-traveling debugger, which once I get the state externalized and other stuff, then implementing something like that is going to be easier. And also to go further with signals as data so that we can manipulate the whole graph and do graph transformations on it. And other ideas. Special thanks to Rich Hickey, David Nolan, Alex Miller, everyone else who put so much time and effort into Clojure, Evan Czaplicki for Elm, and very special thanks to my wife, Julie Hache, who has been incredibly supportive and encouraging through all of this. Thanks very much.